Module 1.2, Electric Force. You have learned in the previous module that charges with the same sign repel and those with opposite signs attract. These interactions are described by the electric forces between them. A positive charge Q1 will push away another positive charge Q2, and the interaction is mutual, which means that Q2 will also push Q1 away. And by Newton's third law of motion, these two forces are equal in magnitude but opposite in direction. The magnitude of the electric force between two charges was measured in an experiment done by Charles Augustin de Coulomb. He found out that the magnitude of the electric force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. This is neatly summarized by this equation, which then came to be called Coulomb's law. The constant K is just a proportionality constant with the value of 9 times 10 to the 9 Newton meter squared per Coulomb squared. Because of this scientific achievement, the SI unit of charge is named after Charles Coulomb. Note that Coulomb's law contains the absolute value sign. This means that your calculated value will always be positive since you are just calculating the magnitude or length of the force vector. If the interaction is attractive such as the one between a positive and a negative charge, then the two charges will pull each other towards themselves. Note that Coulomb's law is only for calculating the magnitude of the force vector, and the directions of the forces are always along the line connecting the two charges. If there is more than one force acting on a charge Q, such as the one shown here, then the principle of superposition of forces will be applied. The total force on that charge will then just be the vector sum of all the forces acting on it. Now let's have some examples. In this problem, we have two charges with opposite signs, which means the electric force is attractive. We are then asked to find the magnitude and direction of the force exerted by Q1 on Q2 and vice versa. Note that these two forces are equal in magnitude but opposite in direction by virtue of Newton's third law of motion. For the first problem, the direction of the force exerted by Q1 on Q2 is directed towards Q1 or to the left. Note that Q1 will pull Q2 towards itself since opposite charges attract. Knowing the direction, we solve for the magnitude using Coulomb's law. We then substitute using the given values. Note that we converted the given units to standard units, such as the nano prefix, which means times 10 to the negative 9. We then get a magnitude of 9 times 10 to the 9 newtons. Since we already know the direction, then the force exerted by Q1 on Q2 is 9 times 10 to the 9 newtons to the left. Alternatively, we can write this in terms of vectors, and the force vector is negative 9 times 10 to the 9 newtons I hat. For the second problem, the direction of the force exerted by Q2 on Q1 is towards Q2 or to the right. Again, we use Coulomb's law to solve for the magnitude. In this case, you will get the same magnitude as the force exerted by Q1 on Q2. Knowing the magnitude and direction, the force exerted by Q2 on Q1 is 9 times 10 to the 9 newtons to the right, or in vector form, 9 times 10 to the 9 newtons I hat. Let's now have an example where there is more than one force acting on a charge. In this problem, there are three charges Q1, Q2, and Q3. Q1 is located at y equal to 1 nanometer, Q2 is at x equal to 2 nanometer, while Q3 is at the origin. We are then asked to find the magnitude and direction of the total force on Q3. There are only two forces acting on Q3, the force exerted by Q1 on Q3, F13, and the force exerted by Q2 on Q3, F23. The total force is then the vector sum of these two. Q1 will push Q3 down, while Q2 will pull Q3 to the right. In terms of vectors, these forces are given as these. The total force vector will then be located in quadrant 4, and we expect the direction or the angle to be between 270 and 360 degrees. Knowing the directions of each component vectors, we are left to solve for the magnitudes. Using Coulomb's law, we get the magnitude of F13 and F23. Note that we didn't place the units here and instead placed the final unit, newtons, at the end. You can do this if and only if you have converted the given units to standard units. The total force vector in standard form is then given as these. Note that the vector has a positive x component, F3x. At the same time, the y component, F3y, is negative, implying that this vector is located in quadrant 4. To solve for the length or the magnitude of this vector, we use the Pythagorean theorem. Doing this gives us a magnitude of 9.28 times 10 to the 9 newtons. For the direction or angle theta, we use the tangent inverse of the y component over the x component formula. We then get negative 75.9 degrees. This angle is equivalent to 284.1 degrees in standard angle measurement. These results imply that the charge Q3 will likely be pushed or moved towards quadrant 4. But this is only possible if the charges Q1 and Q2 are fixed in their locations.